using forces method to find the forces in statically indefinable frame. This is article number 3.13 from the book Mechanical Systems Calculations of the Marine Facilities. We have the sample and the exercise. Exercise is it is assigned the statically indefinable frame. We can see the frame on the figure 3.13a on the left, and this is 2 times statically indefinable frame. The height of the frame 6 meters. The left end of frame embedded in the point A. This is rigid embedding. And on the right, at the span of 4 meters, we have the fixed hinge B, and the height is 6 meters, as I told. And in the middle of the beam, or the up beam, horizontal CD, applied the external force concentrated 8 kilonewton. This is a sine system. And on the stand, AC of the frame, rigidly connected to the horizontal beam CD and to the right one stand DB. To the left one stand, we have the applied distributed load of the intensity of 2 kilonewton per meter. Okay, so it is assigned to determine the support reactions of this statically indefinable frame, and to determine the diagrams of the bending moment of the shearing transverse forces and on of the longitudinal forces acting in the elements of the assigned mechanical system. First of all, we have to define what is the main system. Main is a statically definable system which corresponds to the assigned system, statically indefinable. We decide that statically definable system could be if we cut out the links to the hinge B. We have 2 links here, there is fixed hinge. And instead of the hinge, we, to the point B, apply 2 forces, 2 unit forces, x1 and x2. This is not the unit forces, this will be unit forces when we will determine the factors in the canonical equations of the force method to find these reactions, magnitudes of x1 and x2. Actually, this is the reactions, not unit forces. Okay, so after determination of the main system, as could be indicated on the right one, diagram 3.13b, we have to determine the factors in the canonical equations of the force method, and the three terms in the canonical equations of the force method, as we have 2 times statically indefinable mechanical system assigned. So we have 2 canonical equations in the system. For determination of the factors, this is delta log case 1, delta log 1, 2. This is displacement and action of the unit force applied in the directions of the unit forces, in the direction of the force x1 applied instead of the cutout horizontal link to the point B, and delta log case 1, 2 in the force direction on behalf of the action of the unit force in the direction of the force x2, and free summer. This is a displacement in the force direction of the force direction is that direction of the force x1 instead of horizontal link of the connection, horizontal support link of the connection to the hinge B. And the second canonical equation is that the 3 summons, the first is the product of the displacement and action of the unit force. The second factor in each of the first 2 summons are the magnitude of forces subject to determine. We don't know, it's unknown variable, so they have to determine this while deciding the system of the canonic equations, but to decide this canonic equation, first of all, we have to define what is the factors in the summand and the free summand in the canonic equation. Delta log case 2, 1 is the displacement in the direction of the applied second force instead of the cut of second link to the point B. If second force is and action of the unit force in the direction x1 plus factor delta log case 2, 2 is unit displacement at the action of the second force in the direction of the application of second force, but on the action of the unit force in the direction of second force. And the sorry, and the delta uppercase 2f is free summand in the displacement in the direction of the application second force and the action of the external load. External load, we have the concentrated load h kilonewton and distributed load for 6 meters of 2 kilonewton per meter. So finding the factors in the canonic equations of the force method. To find the factors of the canonic equations, it is effective to use the more integral for finding of the displacement, and which is usual, and to find the more integral of the product of the diagrams in the numerator of and the integral, so in the integrand of each integrals. So we have to find the product of the of one of diagrams area on the magnitude of another one diagram, which corresponds to the center of the first one. Taken, for example, the area of the diagram using the Vereshchagin rule. If one of the diagram is of the linear shape, so we can use the Vereshchagin rule. This simplifies to finding the displacement and action of the forces. Anyway, to find the displacements, first of all, we have to have the diagrams of the bending moment of the efforts under which we have to find the displacement. And if the forces and the unit forces and the external load are applied to the main system. Main system, this is statically definable system, determined of the assigned statically indefinable system. So to use Vereshchagin rule, first of all, we have to determine the diagrams of unit forces applied in the direction x1 and x2, and the diagram of the bending moments and action of the external load and action of first force x1 of unit force in the leftward direction to the point B of the main system. We can find the reactions in the point A, the components of the resultant force in the point A of the support, and the components of the bending moment in the support A and action of the unit force. So the bending moment here is 0 because the force acts in the direction line of the action of the unit force x1 passes through the point A. So the force do not cause the bending moment around the point if the line of the action of force crosses this one point. But the section of this force for the arm 6 meters of the height of the frame, we have here the bending moment equals 6. 6 is product of the arm 6 by 6 meters by 1. This is magnitude of unit force, and we determine the diagram on the stretched fibers of the vertical stand, right one vertical stand. And the diagram bending moment is even distribution of bending moment for the upper beam of the assigned and the main system mechanical. Due to this is parallel force to this beam, the arm of bending moment for each beam is equal to 6. And for the second one stay from the point A to the point C, A to C, is a direction of the unit force x1 is a linear diagram, and we have 2 points. This is a rigid connections of the elements of the mechanical system, AC and BD. So the moments are transmitted through the connection of the beams. And so we have from 0 to 6 a linear diagram of the bending moment. This we have the diagram of the bending of the main system and action of the force X. The diagram of bending moment action of the force X2 in the direction, the upward force applied to the point B, and on the stand, the BD stand, vertical one stand, we have zero diagram bending moment as a force X2 acts along the line of this vertical stand, so we do not have the bending moment in it. In the horizontal upper beam of the frame, we have linear diagram as we do not have the distributed force when we consider the action only the force x1. So this from 0 to 4, we have 2 points enough to have the linear diagram of the bending moment. And this point is a rigid connection of 2 elements mechanical system. So this point transmitted the bending moment through the connection of the element of mechanical system. And we have the even distribution 4 of the bending moment from the point C, as I remember. Yeah, C to the point A. Okay, so this is a diagram of the bending moment at the action of the force, unit force x2 equal 1, applied to the point B upward. And we as well can find for the expected check of the found result the total unit diagram. Sometimes we have to do the verification. For the verification, it is effective and logical to find the total diagram of the previous two. Just we have a total of this one and this one diagram, and this is indicated how to. This is a linear diagram for each of the elements of mechanical system. The enough is only 2 points for this linear diagram to determine it. 2 points is the ends of the diagram. For the each element of mechanical system, the diagram of the total diagram of unit forces, total unit diagram is of the trapezoid shape or maybe triangle shape or the twisted trapezoid like here. So only 2 points we need, and these points in each nodes here in supporting nodes, we have the magnitudes taken from the previous 2 diagrams, and the total of these magnitudes, the 4 here, 6 and 4 here with other signs. So we have 2, 6 minus 4, we have 2 transmission of the bending moment for the total unit diagram, and to the 6 is here, because we have 0 here and the 6 here and the 6, and etc. So we have a total unit force diagram, and the diagram of the bending moment action in the assigned, in the main system of the assigned frame and the action of the external load. So first of all, we have to find the support reaction in the point A and action of the external load is distributed load Q of the intensity 2 kilonewton per meter and the concentrated force H. So the bending moment is the concentrated force, and state this force is, if concentrated, we have to find 6 meter per, to me is a force equal to 12 kilonewton applied in the middle with the arm rotating clockwise with 3 meters. 3 meters is half of the height of this mechanical system. So 12, the force applied here of the distributed one, if we consider like concentrated, 12 for 2 meter is rotating clockwise, is 24 Newton by meter, and this one applied with arm 2 meter around the point A, force H. So this is H product by 2 is equal to 16. Rotate in the same direction as the distributed force. So we have here together 52. 52, the magnitude of the diagram of the bending moment and action of the concentrated force to the middle of the up one beam and to the middle of the left one stand. But on the stand as well, excuse me, first of all, the second, and to the second of this trapezoid, the stroke line trapezoid. So we have 16. Why 16? Because the action of the concentrated force here is H and arm is 2 to the left one and 16, and this is the rigid end. So the 16 transmitted to this stand. So we have 16 here and triangle shape of this segment of the diagram and 16 here. But this is a parabolic segment, a square parabolic segment due to the application to the stand AC of the distributed load. The parabolic segment 9 equal in the middle. So if it would be the linear diagram of the trapezoid shape, this is 16, 52, 52 plus 16 is 68, 68, and divided by 2, 68, 68 divided by 2, this will be 34, 34. And so we have to find this, how much remained here, minus 9, yeah, okay, and for the distributed load, the maximal the paraboloid shape diagram here will be the product of this cube by the square squared length of the application of the distributed force squared is 6 and to the power of 2 divided by 8. This is if we assume that toward the action of the distributed force, we have the bending moment parabolic diagram here. For example, even we have the supports in 2 points. And this is, segment H will be 9 kilonewton by meter. 9 kilonewton by meter here have to be. And after that, we have to find the factors of the canonical equation of the force method. The factors we indicated the lowercase delta 1 in the direction 1 and direction of the force 1. So we have to find the more integral in the integrand. We have the fraction in the denominator. This is the characteristic of rigidity of the transverse section, model of elasticity of the material and the moment and inertia of transverse section. And in numerator, we have the product of the diagrams as we consider the displacement in the direction of the application of the unit force x1 equal to 1 and the action of the same force. We have to do the product of this diagram by itself. We do the total by the elementary mechanical system. So we have the elements of the mechanical system, and the first element area is 6 by 6, 6 by 6, and this is area of the triangular diagram, and the two-third is ordinate of this element, and action in the, corresponding the center of the area of this element. So for the triangular shape, the center area located 1/3 part from one leg of this triangular shape, and the 2/3 part to the vertex of the triangle shape. So as the total length of the second leg is 6, so 1/3 is 2. So we have 2, 3. Okay, 2, 3 from the beginning. So the magnitude here will be the diagram of the bending moment and action unit force will be for the center of the area of this diagram. Magnitude will be 2/3 product by 6, and this we have 2 on 2 stands, on the left one, the right one, so the same here multiplied by 2. And for the horizontal element of the mechanical system, we have the product of the 6 magnitude by 4 meter the span between these two nodes of the mechanical system is the area of this diagram, and 6 is the magnitude in the middle of this area, magnitude 6 as well. So to the substitute in the equation of the magnitudes, we have that unit displacement in the force direction of action of the unit force x1 and the action of the same force is like 288 divided by E and I. Oh, we have just a little bit transform for next more convenient transformation is equal to H64 divided by 3 modulus of the elasticity of the material and the moment of the inertia of the transverse section of the element mechanical system assigned the same for each element mechanical system. I mean the rigidity characteristics of the transverse section. And the second factor in the canonic equations of the force method is finding the displacements delta low case 1, 2 and delta case 2, 1. These two displacements are reciprocal, so they have to be equal. And we can find in the sequence of by the total of each of the elements of the mechanical system, and this will be the fraction in the integrand of the product in the numerator of the area of one of diagram by the ordinata corresponding the center of the area of the first diagram, ordinate of the second diagram have to be by the Vereshchagin rule, as we can do due to the diagrams are of the linear shape. Vereshchagin rule is applicable for the diagrams of linear shape. So using this diagram, we can find that it's equal to minus 6 plus product by 4. This is the area of this one, even distributed diagram of the bending moment on the upper beam of the mechanical system. We have sign minus due to the moments of this diagram, the magnitude in the middle of the second one diagram here is 2, just half of 4. In the middle of this span, we have the magnitude of second diagram 4, but we assume that these two diagrams are determined on the other layers of the element mechanical system. This is a stretching of the upper layers, this is stretching of the lower layers of mechanical system because of the direction of the applied unit forces. So we have minus due to other signs of these two diagrams. And the minus we have for the product of this one left diagram triangular to this even distribution bending moment of the 4 and action of the force unit force x2. And we have minus 2 due to these diagrams as well have two diagrams have the another signs. So minus half product by 6 by 6 and by 4. So then we 1/2 by 6 by 6. This is the area of the triangular diagram. 6 and 6 is the h of this diagram, and the area of the triangle is 1/2 of the product of the two sides of the triangle of the base and length and the h of the triangle. And 4 is the magnitude of the bending moment in the middle due to in any point because this even distribution is point of the area of this one diagram is one third part from the point of the this rigid end, and the two-third part from the support to the point of the center of area of this one diagram. So for this we have four bending moment with other sign of other diagram too. So this is a product of two diagrams, and we have after the substitute minus the fraction of 120 divided by E and I, E and modulus 60 and uh, moment of the inertia of transverse section, so characteristics of rigidity of the element mechanical system section. As well as in the previous one, for us for future transform is convenient to have the denominator 3 as well. So we have the same as equal to 360 divided by 3 by E and by I. And the next force factor in the canonical equation of the force method is that finding the unit displacement and action of the unit force x2 in the same direction, displacement as x2 and action of the force x2. So this is a product, the diagram of the x2 by itself. And we have in the brackets, when we derive the common factor out of the brackets, in the brackets we have the product of the area of this one triangular diagram is half of product by 4 4 is a span and 4 is magnitude maximal. And the two-third part of the same diagram, two-third because the center of the area of this triangular shape is one third part from one to one side and the two-third to another one. And the magnitude here is two-third by multiplied by 4. And the product of the area of this one, diagram of even distribution of bending moment in the stand, is length is 6 meters, the magnitude is 4, so we have 6 by 4, and by 4 is a magnitude in the center of the area of this day. Okay, and finally we have 3, 5, 2 divided by 3 by E and by I. So we found the factors of the canonical equations of the force method. And we need to find as well two independence. First of all, we have to make a check, the verification, and after that we can find the three summands of the canonical equations. To the check of the correctness of finding of the factors, we can use, for example, the diagram of common of total unit displacement, total unit. This is a total of these two previous one diagrams. We can see, and let's find the displacement of the generalized unit force and action of the generalized unit efforts to the direction of the generalized unit effort. So the product of the diagram of the total diagram of unit force to each other. What is the result of displacement? This is abstract concept of the displacement in the direction of the total of this one displacements here. It is equal to total of delta 1, 1 plus delta 2, 2, just algebraic total. Excuse me, is of all total of all displacements delta 1, 1, delta 1, 2, delta 2, 1, and delta 2, 2 have to be equal together to the displacement in the generalized direction and the action of the generalized forces x1 and x2. And we do this using the total unit force diagram. Total unit force diagram. So consider this diagram. First of all, we consider that we have the summons. One summand for this one. This trapezoid, this is twisted trapezoid. So For the first, we have 6 by 6 by 1, 2 part is the area of the diagram bending moment on the right one stand. This is magnitude of the same diagram corresponding the point of the area of this diagram. Next is the 2 fourths part is finding the area of this one diagram, and in the middle that we have here 4, but for the trapezoid rule we can find this like using the trapezoid rule. We do not use the as a two products of this in this definite one summand we use the trapezoid rule equal to two products of the diagram magnitude on the one end and the 2 plus 2 products of the 2 by 6 by 2 products by the diagram on the another hand, and the cross multiplication. Cross multiplication we have like the factor 1 from the trapezoid rule, product by 2 by 6, factor 1 by 2 by 6, and factor 1 by 6 by 2. So actually this is a second summand inside of the first summand we do by the Vereshchagin rule, the second summand we do by use of the trapezoid rule, and the next one is a factor before the brackets of the second summand in the general brackets. This factor is the length of the beam considered one. We have 4 for the upper one beam divided by 6. 6 is the denominator from the trapezoid rule. The 6 denominators in the last one summand under the general brackets. And this is 6 length of the stand. So we consider the stand this one using the trapezoid rule as two products of these two products of these two, and plus 2 products of this 4, and minus 2 products by 4. Is why minus, because the 2 and 4 are of the other sides, and here have to be minus 2. Sorry, as well. This may be a little bit, or have to be minus, and minus 2 by 4. So this is the use of trapezoid rule. So now we have the result of the check as the fraction 496 divided by 3 by E by I. And when we consider the total of previously found unit displacement, there will be the same, 496 divided by 3 by I. So this is confirmation of the correctness of finding of the unit displacement, which are at the same time the factors and the canonical equations of the force method, the deformations compatibility concept when determining the statically indefinable mechanical system. As well, we could do the line check in definite one direction addiction of the forces applied to the another. So, but we do not need to do that, because the confirmation of the first one check, this general approach of the verification, gave us the confirmation of the good results of the unit displacement. So we no need to do the line check for finding of the displacement in any direction at the bending moment of the forces applied to other possible directions. Unit force total applied to other directions. So next we are finding the free summands of the canonical equations of the force method to find the free summands, like here delta uppercase 1f and delta uppercase 2f. So displacement in the cutoff links in the first one direction, second one the direction of the external load, and we use in each case the diagram of the bending moment and action of unit force in the direction 1 for finding the free summand delta 1f, and we use the diagram of the action of unit force in the direction 2 for finding the free-summoned delta 2f. And for both summons, we have to use the diagram of the bending moment under the action of the external load. To do that, we consider first the product of this one segment by the magnitude 6, the area of the segment is 16, and the extent is half of the span between C and the D points is total distance is 4, so half of is just only 2, and the diagram is of triangular shape, so we have 1, 2 of 16 and half of 16 by 2 by 6 is the magnitude of the bending moment in this one diagram corresponding to the center of the area of the previous one diagram. We use the Vereshchagin rule, but it's even distribution, so respectively the location of the section, we have the same magnitudes for all the horizontal span, all horizontal beam. And we next consider as well the trapezoid rule to find the, so it's combining. Trapezoid rule, we multiply the, for the trapezoid rule, we have to, sorry, span is 6, 1/6 part of 16 by 6 plus 4 multiplied by 17 by 3. No, excuse me, this is not trapezoid, this is Simpson rule. This is Simpson rule. We have the product of the diagrams on the left plus 4, the product in the middle of the diagrams, the Simpson rule we use. 17 we product by 6. 17 by 4, 4 is the factor of the Simpson rule, and by 3. And by 3. And by 3. By 3 here. Here is a diagram corresponding the 17 diagram. Here we have 3, in the middle we have 6, we have 16. This 16 by 6 with factor 1, 17 the diagram magnitude of the bending moment and action of the external forces. By 3, 3 is magnitude of the diagram of the bending moment and action of force, and 52 product by the diagram of the with a factor 1 to 0. 0 due to the magnitude of the diagram bending forces and action of the unit forces 0. So by the Simpson rule we have only 2 summons, and finally we have the result that the free summon is equal the fraction 1188 divided by 3 by EI, and the displacement of the in the direction of the second force as a direction, second force upward, force applied to the point B, and action of the external load. So we have to multiply these diagrams to the diagram of the bending moment here, and action of the external force by the diagram of bending moment action of the unit force in the direction of the second force x2. And here we have the product is the first is a rule of the Vereshchagin. So we have minus 1 second of 16 by 2 is 16 by 2 is this area of the segment of diagram. Segment of this diagram, 1 second, the 2 is distance of from C to the point in the middle. The total span is 4, so C is 2, and 16 by 2 by the 1/2 is for the triangle shape of the diagram. And here we have the magnitude. Magnitude using the Vereshchagin rule for the here is magnitude located found 1/4 is 1/3 part for the 2, so very small segment here of 2, we have 1/3 part from the point C to the center of the action, center of the diagram of the bending moment. So the magnitude is 2/3 by 4 plus 1/3 by 2. So this is a magnitude of the bending moment diagram here, corresponding the center of the area of the small segment of the bending moment diagram, the action of the external force. This is, and minus, we have the product of the diagram of the other signs of the bending moment action of the second force and the diagram of the bending moment on the stand AC. We use Simpson rule as well because the diagram is we cannot use the trapezoid rule. The diagram is curvilinear, and it's not so much comfortable to use the Vereshchagin rule as the diagram as well curvilinear is likely to use the Simpson rule. Simpson rule is for nonlinear available if the nonlinear diagram of the degree is no more than 2. Before the second degree of the diagram is applicable, the Simpson rule is the length of the stand, the h of the mechanical system divided by 6 a factor from the Simpson rule diagram, and we have 3 summands. The first summand is the product, perhaps this is absent here, product of 52 by 4, 52 by 4 have to be by 4, excuse me, with the error here, plus 4 is a factor from Simpson rule. It have to be 4, 62 by 4, 4 product by 17 by 4, and 16 by 4 is a product of the 16 by 4, 52 by 4 have to be, and 17 by 4. 4 is a diagram of the even distributed diagram of the bending moment, and we have here, if we do substitute correct here, sorry for the error, this have to be 4. We will have the minus fraction 1792 divided by 3 by E by I. So we have a force we have the second free summand of the canonical equation of the force method. And we as well can determine the verification of the correctness finding these 2 factors. So we first have the total of these 2 factors, and next we will find by use of the Mohr integral of the displacement and action of the force in the total direction of these 2 displacements under unit forces, in the directions of unit forces, using the diagram of the total diagram of of the bending moments and the action of unit forces. We use for the left side, we use the Vereshchagin rule. This is the area of the segment, this one segment product by the very small this magnitude of the diagram of the trapezoid shape or the total diagram of unit bending under unit force, and each is in the brackets here determination of this magnitude because the trapezoid one side is 2, the other side is 6, and the product plus the next summand in this Mohr integral we determined by the rule, the Simpson rule as well. This is span we have this correct with not error 52 product by 6 by 4 is correct, and the plus 4 by 17 by 4 is and then for the middle 4 by 17 by 4, this is area. This 4 it's, excuse me, just have to check. 4 is factor from the Simpson rule. 17 by 1 is a product of two magnitudes. 17 magnitude and 1 magnitude here. In between of this, in the middle of this twisted trapezoid, we can 2 pi 4 minus 2 is 2 divided by 2 in the middle, so we have 1 only. And plus 16 by 2. 16 by 2, we have 16 product by 2. So 52 by 4 by this one displacement, plus 4 by 17 by 1, and plus 16 by 2. Yes, we have. And finally, we have the the displacement direction of the external load in the generalized direction of two displacements in the direction of the one cutoff link and the second one together, just algebraic total. We have for the elastic mechanical system, we have minus fraction 604 divided by 3 by EI. So this is the same. So the correctness of finding the free summons of the canonic equations thus confirmed. Now we have the canonic equations too. We cancel the common factor is 3 in the denominator by E by I. For in the equations, we do not have the denominators for the factors, free summons, and the factors with variables x. And after the substitute, we can find that the magnitude of the force x1 is equal 130 kilonewton, 1.30, and the magnitude of the second force is 6.41 kilonewton. These are forces. And now when we have the forces, we can find other 3 forces. So we originally had 5 times statically indefinable system, and we next determine the main system. Main system, we cut off the unnecessary links of statically indefinable system. We have 2. These links were linked from the support to the hinge B, and we substitute these links by the forces subject to found by the compatibility of the deformations. Rule is the compatibility of deformation is the equations of canonic equations of the force method. Using these equations, we found the magnitude of the forces in the cutoff links of the unnecessary for the statically definable system, and now we have only mechanical system assigned, loaded by the reactions in the point B. This one reaction, the point B, the leftward and the upward reaction, the point B, and loaded by external load. External load, we have concentrated force in the middle of the upper, the beam of the mechanical system. On the left one stand, we have distributed load, but the system is statically definable, and we can find other reactions in the point A, the bending moment in the point A, and the components of the resultant of the force in the point A. After finding of all the reactions, we can determine the final diagram of the bending moment assigned. So what assigned? How we can do that? We can use the got diagram of the bending moment under external load of the main system indicated in the on the figure 3.15.3. This is C. This is M and action of the external force F for the main system. We can use 2 more diagrams. The first one, the corrected diagram of the bending moment and action of the force applied leftward and instead of the cutoff link when we do the main system out of the sign system. But we have to correct it first because the diagram previously did this one on the assumption that this force is equal to 1 because we had objective to find the factors on the action of the unit force, and the x2 is well 1, so we have deltas lowercase factors in the canonical equation, the displacement at the action of the unit force. But after finding the force x1 and x2 magnitudes, we have to multiply this m1 and m2, the diagrams we had, m1 and m2 and the action of unit force. We multiply the diagrams by the scale, by the found magnitudes of the force x1 and the force x2. And we got the diagrams, corrected diagrams we had originally for the main system. And the total of these three diagrams is the diagram of the bending moment acting on the mechanical system. So what is the total diagram? Here we have 52 minus 25, 64. This corrected diagram of unit force M2 by it multiplication to the corrected diagram of M2, this B figure on the action of unit force, but if we have a force x2 equal not 1, but proportionally x2 is 6.41, and we multiply this magnitudes on the diagram by 6.41, the actual magnitude of the force x2, we have this one diagram, and the same as the first one diagram. This is a product of the unit diagram and action of unit force by the got magnitude of the force in the first direction applied to the point B. And we keep going all around the mechanical system, and we have the diagram of the bending moments as a total of these three diagrams we had as indicated in this equation on the slide. For this we have 7.8, we have 25, 16, 64 bending moments, and we have 16, so 7.8 plus 16 minus 25, 64, we have 1.84, etc., etc. So going all around, and just by total of the magnitudes in each definite one point, we found the diagram of the bending moment and action of the as external load on the assigned mechanical system, as the support reactions in the point B found x1 and x2, the horizontal one and the vertical one support reaction. After that, we had to we have to remind that this assigned to find the diagram of the transverse forces and the longitudinal forces. To found the diagram of the transverse forces, we use the mathematical property of diagrams of bending moments and transverse forces, as these diagrams are in the derivative dependence, integral derivative dependence. So as a diagram of the bending moment by each of the element mechanical system, diagram of the bending moment is the integral of the diagram of the transverse forces. Accordingly, the diagram of the transverse forces is for each of the mechanical elements of the system is a derivative of the diagram of the bending moments. We can, if we have no the mathematical equations for the bending moments, we just have only the magnitudes and the general shape of the bending moment diagram. So we use the general the formulas to find the diagram of the bending moment. So as first of all, for the vertical stand AC, in case of evenly distributed load action, we have distributed load action like 2 and the length of the application, 2 is intensity of the distributed load. The formula for the just digital determination, the approximal determination, no approximal, but digital determination of the magnitudes of the sharing forces we can use for the left one if we just rotate this one stand to the horizontal location. So this will be the left one and this will be the right one end. So for the left one end, we have the formula of determination of the magnitude using the diagram of the bending moment and action of the distributed load as intensity product by L divided by 2 plus the fraction moment on the right end of the bending moment diagram with 184 minus the magnitude on the left end 26 36 divided by the length 6 meters. So we have the magnitude of the shearing forces in the point A, the left one point, assuming the rotating of this element to the horizontal location. So after the substitute all of that, we can find using the derivative mutually integral derivative relations of the diagrams of the shearing force and bending moments. We can find that the shearing force here is 10.7. Sorry, it could be here a little bit. 10.3, 10.7 have to be. Sorry for that, and here have to be 10.7. Magnitude in the diagram, just a little bit error in the description of the diagram. And for the point C, the right one end of the stand, if we rotate to horizontal position, there will be the minus the same, and minus the same first summand with the minus sign, only minus 6 plus, and the second summand, and this equal to minus 1.3 kilonewton. So we have here 1.3 on with another sign. And the horizontal elemental mechanical system CD, yeah, and this is a linear diagram. We have the even distribution of the transverse force assigned of the external load. So under the even distribution, the diagram of the shearing forces is linear. For the horizontal part of the mechanical system, we have the even distribution 1.59 got as the magnitude in the middle. We have here the angle of the angle of the fracture of the line of the diagram of the bending moment. So for the first part from 0 to 2, this total length is 4. From 0 to 2, we have the length of the segment 2, and this is magnitudes 5.02 minus 1.84. This is magnitudes of the diagram of the bending moment on the right and the left ends of the small segment of length of 2 meters. So we have the inclination of this diagram for 1.59. Inclination is the tangent of the inclination due to the SS. QCE is a derivative of the bending moment diagram for this definite one element mechanical system in the segment CE. And next is for the section ED, we have as well the right minus 7.8 is another sign. You see with a twisted trapezoid here, this small segment for last 2 meter segment of the element CD is 5 of the another sign, minus 5. We have to assume to consider as well the signs of the magnitude. So we using the formulas of the derivative determination by the characteristics of the diagrams at the ends for the linear diagrams and for even distributed diagrams. And we as well have to consider the signs of the magnitudes of summands in the numerators in these diagrams as well, besides of the signs of these formulas themselves. So we have minus 7 plus 8, as this is of the another sign. The sign here is positive. And minus positive 5.02. So minus positive is this minus, and minus due to the magnitude is of the another sign, then 5.2 on the diagram. So we have minus 6.41. This we can do the check immediately as this one step from 1.59 to minus 6.41 means the application of the force of H in this total 1.59 plus 6.41 is equal to the application of the concentrated force in the definite one place. Yes, it was assigned 8 kilonewton force here. And for the right one end, we can find the diagram of the shearing forces equal to 7.h minus 0, 7.h minus 0 equal to 1.3. So this is diagrams of the shearing forces. Yes, and the diagram of the longitudinal forces. To find the longitudinal forces, usually we have to cut off the nodes. So we consider the nodes and the balance equations for the nodes. For one node point C, we consider the transverse forces. We know from the diagram of the transverse forces, and we have to find the diagrams of the longitudinal forces. They have to be in the balance in the nodes for this definite one. Is for the rigid connection, but not so much important here, so we do not consider the bending moments here, only forces. We indicated the longitudinal forces here for the case of the rods stretching, not compression. But after finding this magnitude due to the balance of the forces indicated on this scheme 3.15.5a, or the balance of the node C, we found that the magnitudes are negative. So assigned as stretching of the this stretching action on behalf of the elements of mechanical system to the directions mean the stretch of this mechanical system. They stretches and acts in this direction on the node. But we found that the magnitudes are negative with a minus sign. So actually the nodes experience compression. So for this one we have 1.3 minus 1.59 minus the compressed element mechanical system. And for the node point D, as we have no longitudinal forces distributed along the CD segment of mechanical system, so we have the indicated on the scheme forces, and due to the balance, the vertical force in the acting in the second stand, as we have second stand dB, we have the force compressed 649 due to balance of the node. And the questions and comments. The system of canonical equations method of forces for a doubly statical and indefinable mechanical system consists of two equations, and each equation consists of two summands with the unknown variable subject to find, and the factors to the variables equal to the for the first equation for the displacement under direction of the unit forces, first and the second in the first direction, and the free summand in the first direction is the displacement and direction of the external force in the first direction, and the second equation is the total of all displacement and action in the second direction of the cutoff link, and second cutoff link, cutout link, and as well two summands of the displacement in the direction of the cutout link second, and action of the unit forces applied, or the unknown forces. But the factors are the displacement and action of the unit forces and the free sum and the displacement and action of the external load in the same second direction. 3.13.2 finding the coefficient of the canonical equations of the method of forces, the displacement and the action of the unit forces in the direction of the replaced connection during the formation of the main statically definable mechanical system. To find the coefficient of canonical equations, we use Moore integral. Moore integral is a product of the diagrams of the bending moments for the frames. And if we consider the frames, yes, we did consider the frame. And this is a bending moment and the action of the unit forces when we found the factors of the summands of the canonical equations with the variable subject to find. And the product of the diagram of the bending moment and of the in the main system. Main system is the statically definable system, which corresponds the assigned system, but statically definable just by the cutoff the unnecessary links in the assigned system. And the free summands and canonical equations mean the displacements by the in the directions of the cutoff links by the action of the external load assigned for the assigned system. 3.13.3 determination of Moore integral by multiplying the diagrams using the Vereshchagin method as the product of area of the one diagram by the ordinate of another diagram, the rectilinear in projection and the center of area of the first diagram. Yes, it is. If one of the diagrams, maybe the diagram of the bending moment and action of unit forces on the main system are linear, so we can use Vereshchagin method. If we have no linear diagrams, we can maybe use the Simpson method. If two diagrams are linear, as a diagram of the force caused the displacement and the diagram of the bending moments and the action of the unit, force and the displacement in which we finding the displacement. If two diagrams are linear, we can use the trapezoid method, Simpson method for nonlinear, and the Vereshchagin rule in any case. But we have to find the area of one diagram and the magnitude of the second diagram satisfying the in the projection connection of the center of the area of the first one diagram. 3.13.4, the universal verification of the correctness of finding the total of displacement under the action of unit forces, and the line-by-line verification of the correctness of determining the coefficients of canonical equations of method of forces. This is important to do the verification, and we can do line-by-line verification as and for example, we can do the total unit bending diagram. This is mean that the algebraic total of all found displacement and action of unit forces have to be equal of the use Moore integral for determination of the displacement in the generalized direction using the diagram of the bending moment and action of unit forces. If we use the total diagram, so of all unit forces diagrams, bending moments, we add together in the unit one diagram and use this diagram to find the displacement. This found displacement have to be equal to total of all displacement if we found this displacement in each of the directions separately. If we found like the factors of the canonical equation of the force method. And sometimes we have to do the line-by-line verification of the correctness of determine the coefficient of canonical equation. 3.13.5, finding the terms of canonical equations of the method of forces independent on reactions in the replaced connections. the displacement and the action of an external load. The three terms of canonical equations are finding by use the product of the diagrams of the bending moment of the main system and the action of the external forces by the diagram of the bending moment and action of unit force in the direction in which we have to find the displacement of the point of the main system and the action of the external load. 3.13.6 column by column verification of correctness of determining the terms of canonical equations of method of forces and the action of the external load dependent on reactions of connections replaced during the formation of the main system. Usually, if we have now the confirmation of the correctness of finding the displacement by the universal approach when we use the total unit bending moment diagram, we have to find column by column verification of the correctness determined in terms of the canonical equations. 3.13.7 solving the canonical equations of the method of forces determining the reactions of the correctness of the connections replaced during the formation of the main system and determining the resulting diagram of bending moments as the sum of bending moment diagram under the influence of the external load and under the influence of reactions in the replaced connections. After finding the reactions of the unnecessary connections of statically indefinable system during using the rule of the deformations compatibility by the method of maybe use the canonical equations of the force method. So after that, we can determine the diagram of the bending moment as the sum of the diagrams of bending moment of the external load acting on the main system found found from the assigned system by the cut of the unnecessary links, and plus the diagram of the bending moment under unit forces. Corrected the unit forces diagram we used for finding the factors in the canonical equations, but we consider the unit forces, and after decision of the canonical equations we have the magnitude of the forces in the cutoff links, and the diagrams used on the action of the unit forces we have to correct first by the proportional to the magnitudes of the found efforts, maybe forces or moments in the cutoff links. So the diagram of the bending moment finally is the total of the diagrams of the bending moment of the main system and action of the external load and then the action of the loads applied in the cut off the unnecessary links when doing the main system of the statically indefinable assigned system. This will be the diagram, the resulting diagram of the total of the sums of the external load diagram and the diagram of the bending moments, all diagrams, and the action of the forces found by the cut of the links and using canonical equations. The resultant will be the diagram for the assigned mechanical system, not for the main system, due to we did use the main system only to find the factors and the free sums in the canonical equations. In the next, to find the magnitudes of the efforts in the cutoff links when doing the main system of the signed system, statically indefinable. 3.13.8 determine diagram of transverse shear forces using numerical differentiation of the diagram of the bending moments. The diagrams of bending moment and shear forces are in the interdependence integral and differential, as the diagram of the bending moments is integral of the diagram of the shearing forces. Exactly, all diagrams we consider by the elements of the mechanical system. And the diagram of bending moments accordingly is the derivative of the diagram of the diagram of shearing forces is derivative of diagram of the bending moments. And we can use the rules of finding the magnitudes of the diagram of one diagram using another one by the numerical differentiation diagram of the bending moments. For example, we can find for linear diagram of the shearing forces, this very convenient and easy way to find the magnitudes. The use of diagram transfers the shear forces and the balance conditions of the mechanical system at any node to determine the diagram of longitudinal forces. To determine diagram of the longitudinal forces, if we have no distributed longitudinal forces, usually this is we have to cut off the nodes of the mechanical system and consider the balance of the nodes and action of the if concentrated forces may be in the nodes, but actually we have transverse forces in the nodes. After using the balance equation, we have the longitudinal forces as well. And assuming that if we, in the absence of the distributed load longitudinal, which is usual, the diagrams of the longitudinal forces are linear, or likely the even distributed longitudinal force along the elements of mechanical system. So we need only one or two points of the diagram ordinate to have the diagram longitudinal forces linear. Thank you.